There is a region of space that looks empty. For a long time, astronomers assumed there was nothing worth studying there, but NASA kept watching it anyway. In 2012, something unprecedented happened. A spacecraft crossed that boundary, then another followed. What they detected on the other side didn't match our models of space, and it forced scientists to rethink what the edge of our solar system actually looks like. This is why NASA has been watching an empty region of space very carefully. Most people would say it ends with the planets, maybe Neptune, maybe Pluto, if you're feeling generous. But that's not quite right. The sun doesn't just give us light and heat. It also produces something called the solar wind. This is a continuous stream of charged particles that flows outward from the sun's surface at incredible speeds, between 300 and 850 kilometers per second. That's fast enough to cross the distance from Earth to the Moon in less than 2 hours. This solar wind carries the sun's magnetic field with it, and as it flows outward, it creates a bubble around our entire solar system, a protective shield that deflects most of the cosmic radiation and interstellar particles trying to reach us from deep space. That bubble is the heliosphere, and the edge of that bubble, the place where the solar wind finally stops and interstellar space begins, is called the heliopause. Now here's the thing. For most of human history, we had no idea where the heliopause was. We had theories, we had models, but we'd never actually touched it. That changed in 1977. 2 spacecraft launched from Cape Canaveral within weeks of each other, Voyager 1 and Voyager 2. Their primary mission was to explore Jupiter and Saturn, maybe Uranus and Neptune if they were lucky, but someone had a bigger vision. These spacecrafts were designed to keep going, to push past the outer planets and head toward the edge of the solar system, to see how far they could travel before the solar wind gave out. These are the only 2 spacecraft that have ever made this journey, and the data they sent back revealed something fascinating. The heliopause isn't where we expected it to be, and the region just inside it, the place we're calling an empty region, is far more complex than anyone imagined. Let's talk about what Voyager actually found out there. Before they reached the heliopause, both spacecraft encountered something called the termination shock. This is the point where the solar wind suddenly slows down. Think of it this way. The solar wind is moving outward from the sun at supersonic speeds, but eventually it runs into resistance. The pressure from interstellar space pushing back. When that happens, the solar wind crashes into itself like a wave hitting a wall. That's the termination shock. Voyager 1 crossed the termination shock in 2004 at 94 astronomical units from the Sun. Voyager 2 crossed it in 2007 at 84 AU. And immediately, the instruments on both spacecraft registered dramatic changes. The speed of the solar wind dropped by half, from about 400 kilometers per second to roughly 200 kilometers per second. The density of particles increased. The temperature jumped by an order of magnitude, from around 10,000 degrees Kelvin to over 100,000 degrees. But here's what's strange. The temperature increase wasn't where we expected it to be. According to models, the solar wind plasma should have been heated to over 1,000,000 degrees Kelvin after crossing the termination shock. Instead, it only reached about 100,000 degrees. That's still incredibly hot by Earth standards, but it's nowhere near what the theory predicted. So where did all that energy go? It went into something called pickup ions. Here's how that works. The local interstellar medium, the space between stars, is not actually empty. It's about 2/3 neutral atoms and 1/3 plasma. The plasma can't cross the heliopause because it's blocked by magnetic fields. But the neutral atoms are unaffected by magnetism. They drift right through. Once these neutral atoms enter the heliosphere, they get hit by solar radiation. That radiation strips away their electrons and ionizes them. Now they're charged particles. And once they're charged, they get picked up by the solar wind and accelerated to incredible speeds. These are pickup ions. And they absorb most of the energy at the termination shock. About 65% of the solar wind's flow energy goes into heating pickup ions. Only 20% heats the thermal plasma. The remaining 15% goes into accelerating more energetic particles. This was unexpected. It changes our understanding of how shocks work in space. It tells us that the heliosphere is not a simple system. It's dynamic. It's influenced by material from outside our solar system in ways we didn't fully appreciate. Now, between the termination shock and the heliopause is a region called the heliosheath. This is the compressed, turbulent zone where the solar wind has slowed down but hasn't stopped yet. It's still flowing, still carrying the sun's magnetic field, but it's squeezed and deflected by the pressure from interstellar space. Voyager 1 spent about 8 years crossing the heliosheath. Voyager 2 spent about 11 years. The heliosheath was 28 AU thick at Voyager 1's location and 36 AU thick at Voyager 2's location. And this is where things get really interesting. The two spacecraft took very different paths. Voyager 1 went north, Voyager 2 went south, and what they observed was completely different. At Voyager 1, the radial speed of the solar wind decreased slowly as it approached the heliopause. Then, about 8 AU before the boundary, it entered a region where the speed dropped to nearly zero. Scientists call this the stagnation region. The solar wind wasn't flowing outward anymore. It was barely moving at all. In some measurements, it was even flowing backward, toward the sun. This was baffling. If the solar wind stopped moving, you'd expect the magnetic field to pile up, to compress. But the magnetic field strength didn't increase. It stayed roughly constant. That didn't make sense. Magnetic flux is supposed to be conserved. If you stop the flow but keep the source pumping, the field should get stronger, unless something else was happening. Unless the magnetic field lines were being twisted or reconnected in ways we don't fully understand. Voyager 2's experience was different. Its radial speed decreased slowly and steadily all the way to the heliopause. There was no clear stagnation region. The flow remained outward until the very end. Why the difference? One possibility is that the heliopause itself is not static. It moves, it ripples, it responds to changes in the solar wind and to pressure waves from the interstellar medium. And depending on where you cross it, you might see very different conditions. Another possibility is that magnetic reconnection is happening in the heliosheath. When magnetic field lines with opposite directions come close together, they can break and reconnect. This releases energy. It creates turbulence. It might explain why Voyager 1 saw what it saw, but we're still not entirely sure. Let's talk about the journey through the heliosheath in more detail. Both Voyager spacecraft spent years crossing this region, and the data they collected reveals a complex, turbulent environment that changes constantly. The magnetic field in the heliosheath doesn't point in a single, stable direction. It follows what scientists call the Parker spiral pattern. This is the shape the sun's magnetic field takes as it's carried outward by the solar wind and twisted by the sun's rotation. Imagine water flowing from a rotating sprinkler. The water streams out in curved paths because the nozzle is spinning. The sun's magnetic field does something similar. It spirals outward, creating a pattern that extends throughout the heliosphere. In the heliosheath, this spiral pattern persists, but it's compressed, deflected, disturbed by turbulence and pressure waves. The azimuthal angle of the magnetic field, the direction it points in the plane of the solar system, alternates between roughly 90 degrees and 270 degrees. This alternation marks sector boundaries, places where the magnetic field switches from pointing in one direction to pointing in the opposite direction. These sector boundaries are related to the heliospheric current sheet, and they matter because they affect how particles move through the heliosheath. When Voyager 2 was below the heliospheric current sheet, it spent months in what scientists call a unipolar region. The magnetic field pointed in only one direction. No sector boundaries, no alternation. And during this time, the intensity of energetic particles was lower. The environment was calmer. When it moved back above the current sheet, into the sector zone, the particle intensities increased. The environment became more dynamic. Magnetic field lines with opposite directions came close together, creating opportunities for reconnection. Reconnection is a process where magnetic field lines break and reform. When this happens, energy is released, particles are accelerated, the plasma heats up. It's one of the most important processes in space physics, responsible for solar flares, auroras, and many other phenomena. Whether reconnection is actually happening in the heliosheath is still debated. Some observations suggest it is, others suggest it isn't. The truth is probably somewhere in between. Reconnection might be happening in some places at some times, but not everywhere all the time. But the mystery of the magnetic field direction remained, and it tells us something important about the boundary between the heliosphere and interstellar space. That boundary is not clean, not simple. It's a complex transition region where the two environments interact and influence each other. The plasma oscillations that Voyager 1 detected weren't random. They were triggered by specific events, shocks driven by solar transients reaching the heliopause from inside. When a pressure pulse from a coronal mass ejection hits the heliopause, it pushes the boundary outward. This creates a shock wave in the local interstellar medium. And that shock accelerates electrons, creating beams that generate the plasma oscillations. So even though Voyager 1 is in interstellar space, it's still detecting the effects of the sun's activity. The sun's influence extends farther than the heliopause itself. It reaches into the surrounding interstellar medium, creating disturbances that can be measured tens of AU beyond the boundary. This was completely unexpected. Before Voyager, scientists didn't think solar transients could affect the interstellar medium in such dramatic ways. But the data proved otherwise. The local interstellar medium is not isolated from our solar system. It's influenced by it, shaped by it. And that raises a fascinating question. How far does the sun's influence extend? If shocks can travel tens of AU into interstellar space, what else can make it out there? Do solar particles escape across the heliopause? Do magnetic disturbances propagate outward into the galaxy? We don't know yet, but Voyager is giving us our first hints. One of the most important measurements Voyager 2 made was the temperature of the plasma just outside the heliopause. The plasma instrument on Voyager 2 was still working, unlike Voyager 1's, so for the first time scientists could directly measure the temperature of the interstellar plasma. It was hot, between 30,000 and 50,000 degrees Kelvin. That's much hotter than the expected background temperature of the local interstellar medium. Why? Because the heliopause itself is a source of heating. When the solar wind slams into the interstellar plasma at the heliopause, energy is released. The plasma heats up, and this heating extends outward into the interstellar medium for a significant distance. Over time, the temperature should decrease. As you move farther from the heliopause, the plasma should cool toward the background temperature of about 6,400 Kelvin. But Voyager 2 hasn't traveled far enough yet to see that transition. It's still in the heated zone, the region directly influenced by the interaction at the heliopause. This tells us that the boundary between the heliosphere and interstellar space is not a surface. It's a region, a zone of transition where the properties of the plasma gradually change from solar-dominated to interstellar-dominated. And it reminds us, once again, that space is not empty. Even in the regions between stars, there's activity, there's structure, there's physics happening at every scale. The reason the magnetic field direction didn't change is still debated. One explanation is that the interstellar magnetic field near the heliopause happens to be aligned with the heliosphere's field. Another is that the boundary region is more complex than we thought, with field lines from both sides mixing together. This tells us something important. The sun isn't sitting still in space. It's moving through the interstellar medium at about 26 kilometers per second. And as it moves, it's pushing the heliosphere forward like the bow of a ship cutting through water. The shape of the heliosphere depends on this motion. On one side, the side facing the direction of the sun's motion, the heliopause is compressed. On the other side, it stretches out into a long tail called the heliotail. How long is the heliotail? We don't know. Models suggest it could extend for hundreds of AU, maybe even thousands, but we've never measured it directly. That's one of many mysteries still waiting to be solved. Now let's talk about what else is happening in this so-called empty region. The heliosheath isn't just a quiet zone of slowed solar wind. It's full of activity. It's traversed by pressure waves. These are pulses of compressed plasma and magnetic field that sweep through the region. Where do these pressure waves come from? The Sunday. Even though the solar wind has crossed the termination shock and slowed down, it still carries the effects of solar activity. Coronal mass ejections, massive eruptions of plasma from the sun's surface, propagate outward through the heliosphere. They merge with each other to form merged interaction regions. These are giant structures of compressed magnetic field and plasma that can stretch across billions of kilometers. When these merged interaction regions reach the termination shock, they push it outward. They send pressure pulses into the heliosheath, and those pressure pulses eventually reach the heliopause. When they do, they push the heliopause outward, and they drive shocks into the interstellar medium. These shocks are powerful enough to accelerate electrons in the interstellar plasma. Those electrons create beams that generate plasma oscillations. That's how Voyager 1 and Voyager 2 were able to detect plasma waves in interstellar space. They weren't measuring the background plasma. They were measuring the effects of shocks driven by events that happened on the Sun years earlier. Think about that for a moment. A coronal mass ejection erupts from the Sunday. It travels outward for years, crossing the orbit of every planet, eventually reaching the termination shock at 80 or 90 AU. Then it continues through the heliosheath for another 30 AU, and when it finally hits the heliopause, it creates a detectable signal in interstellar space. The Sun's influence reaches farther than we ever imagined. But there's another layer to this story. The heliosheath is also shaped by particles from outside our solar system. Another crucial aspect of the heliosheath involves energetic particles. These are particles with much higher energies than the thermal plasma, and they play a major role in the dynamics of the outer heliosphere. There are several populations of energetic particles in the heliosheath. First, there are particles accelerated by the termination shock itself. When the solar wind crashes into the shock, some particles gain enormous amounts of energy. They bounce back and forth across the shock front, getting accelerated each time. This process, called diffusive shock acceleration, is one of the most efficient ways to create high-energy particles in space. These shock-accelerated particles have energies in the range of hundreds of keV to several MeV. That's kilo-electron volts and mega-electron volts, units that measure particle energy. For comparison, the thermal protons in the solar wind have energies of only a few keV. Voyager measured the intensity of these particles as it approached and crossed the termination shock. The intensities increased dramatically, jumping by factors of 10 or more, and they remained high throughout the heliosheath. But here's what's interesting. The particle intensities in the heliosheath aren't constant. They vary with time. They're correlated with the arrival of pressure waves and merged interaction regions. When a pressure wave sweeps through the heliosheath, it compresses the plasma. And as the plasma compresses, the particles within it are squeezed together. Their density increases. Their intensity, as measured by a spacecraft, goes up. This creates a pattern of alternating high and low particle intensities. Compression regions followed by rarefaction regions. High-intensity zones followed by low-intensity zones. Voyager 2 observed this pattern very clearly. The data shows strong correlations between plasma density, temperature, magnetic field strength, and particle intensity. When one goes up, they all go up. When one goes down, they all go down. The heliosheath is filled with these pressure waves, these pulses of compressed plasma and energetic particles traveling outward from the termination shock toward the heliopause. And they don't stop at the heliopause. When they reach the boundary, they keep going. They drive shocks into the interstellar medium. And those shocks create the plasma oscillations that Voyager detects. Now let's talk about another population of particles, anomalous cosmic rays. These are particles that were once thought to be cosmic rays, high-energy particles from outside the solar system. But they're actually created in the heliosheath itself. Here's how it works. Neutral atoms from the interstellar medium drift into the heliosphere. They get ionized by solar ultraviolet light. Then they're picked up by the solar wind and carried outward. When they reach the termination shock, they're accelerated, but not to extremely high energies, just to intermediate energies, in the range of 10 to 100 MeV per nucleon. That's higher than the shock-accelerated particles, but lower than true galactic cosmic rays, which can have energies in the GeV or TeV range. These anomalous cosmic rays fill the heliosheath. Voyager measured them for years as it traveled from the termination shock to the heliopause. Their intensity remained fairly constant across most of the heliosheath. But at the heliopause, something dramatic happened. The intensity dropped, almost to zero. This was surprising. Scientists had expected anomalous cosmic rays to be accelerated at the heliopause and sent back into the heliosheath. But that's not what happened. Instead, they escaped. They crossed the heliopause and entered interstellar space. Why? We're not entirely sure. One possibility is that the magnetic field configuration at the heliopause allows particles to escape more easily than predicted. Another is that anomalous cosmic rays don't actually need the heliopause to be accelerated. Maybe they reach their maximum energies at the termination shock and then just drift outward until they escape. This has implications for the pressure balance in the heliosheath. If anomalous cosmic rays are escaping, they're taking energy with them. That could contribute to the thinning of the heliosheath, the fact that it's narrower than models predicted. But we're still working to understand the full picture. Anomalous cosmic rays are just one piece of a very complex puzzle. Now, in contrast to anomalous cosmic rays, galactic cosmic rays behave very differently. These are true cosmic rays, particles accelerated to incredible energies by supernova explosions, pulsars, and other extreme events in the galaxy. They have energies in the GeV to TeV range, some even higher, and they're constantly bombarding the heliosphere from all directions. Most of them don't make it through. The heliopause and the magnetic fields in the heliosheath deflect them, turn them away. Only the highest energy cosmic rays can penetrate all the way to the inner solar system. But as you move outward through the heliosphere, the intensity of cosmic rays increases steadily. At 1 AU, near Earth, the intensity is relatively low. At the termination shock, it's higher. In the heliosheath, it's higher still. And at the heliopause, there's a sharp jump. The intensity of galactic cosmic rays outside the heliopause is about twice what it is inside. This jump is one of the clearest signatures of the heliopause crossing. When Voyager 1 and Voyager 2 crossed the boundary, both spacecraft saw the same sudden increase in cosmic ray intensity. It was unmistakable. This has important implications for space exploration. The intensity of cosmic radiation outside the heliosphere is much higher than inside. Cosmic rays can damage DNA. They can increase the risk of cancer. They can cause acute radiation sickness if the exposure is high enough. Protecting astronauts from cosmic radiation is one of the biggest challenges for interplanetary and interstellar travel. Shielding helps, but conventional materials only provide partial protection. And they add weight, which makes spacecraft more expensive to launch. Some scientists have proposed using magnetic fields to deflect cosmic rays, similar to how Earth's magnetic field protects us. But generating a magnetic field strong enough to shield a spacecraft would require enormous amounts of energy and superconducting magnets. It's technically possible, but very difficult and expensive. Another approach is to use biological countermeasures. Drugs or treatments that help the body repair radiation damage more quickly, or genetic modifications that make cells more resistant to radiation. These are all areas of active research. But for now, cosmic radiation remains a major obstacle to deep space exploration. And Voyager's measurements of cosmic ray intensity in the heliosheath and beyond the heliopause give us critical data for understanding the radiation environment we'll need to deal with. Now, here's something else that surprised scientists about the heliosheath. It's thinner than expected. Before Voyager, models predicted that the heliosheath would be about 55 to 65 AU thick, but Voyager 1 measured it at 28 AU. Voyager 2 measured it at 36 AU. Why the discrepancy? Several theories have been proposed. One is that the solar cycle plays a role. The sun's activity varies over an 11-year cycle. During solar maximum, the solar wind is stronger and more chaotic. During solar minimum, it's weaker and more uniform. These variations could compress or expand the heliosheath. Another theory involves charge exchange. Hot ions in the heliosheath can collide with neutral atoms from the interstellar medium. When they do, they exchange electrons. The hot ion becomes a neutral atom and escapes. The neutral atom becomes an ion and gets picked up by the remaining plasma. This process removes energy from the heliosheath and could make it thinner. A third theory involves anomalous cosmic rays. These are particles that originate in the heliosheath itself, accelerated by the termination shock. Some of them escape across the heliopause into interstellar space. When they do, they carry energy with them. This could also thin the heliosheath. Thermal conductivity might play a role too. Heat can flow from the hot heliosheath plasma toward the cooler heliopause. This would reduce the pressure in the heliosheath and allow it to compress. All of these processes are probably happening to some degree, but none of them, by themselves, fully explain the observations. The heliosheath remains thinner than our models predict, and that tells us we're still missing something. Now let's talk about what the heliosheath looks like on different scales. On the largest scales, it's shaped by the global structure of the heliosphere, the termination shock, the heliopause, the way the solar wind flows around these boundaries. This is the structure you'd see if you could zoom out and look at the entire heliosphere from thousands of AU away. But on smaller scales, the heliosheath is full of turbulence. The magnetic field in the heliosheath doesn't flow smoothly. It's full of jumps and filaments. These are sudden changes in the field strength over short distances. They're caused by the interaction between the solar wind and the pressure from interstellar space. They're also caused by reconnection events, where magnetic field lines break and reform. This is what makes the heliosphere so fascinating. It's a system shaped by forces on every scale. From the largest, the interaction between the Sun and the galaxy, to the smallest, the behavior of individual particles and magnetic field lines. Now, there's one more important feature of the heliosheath that we need to discuss: the heliospheric current sheet. This is a thin layer that extends from the Sun's equator outward through the entire heliosphere. It marks the boundary between two regions of opposite magnetic polarity. On one side of the sheet, the magnetic field points in one direction. On the other side, it points in the opposite direction. The heliospheric current sheet isn't flat. It's warped. It ripples up and down like a wavy surface. And as it rotates with the Sun, spacecraft moving through the heliosphere cross it multiple times. Each crossing is called a sector boundary. Voyager 2 spent time both above and below the heliospheric current sheet while in the heliosheath. When it was below the sheet, in what scientists call the unipolar region, the magnetic field pointed in only one direction for extended periods. There was no reconnection happening. The particle intensities were lower. The plasma was calmer. When it was above the sheet, in the sector zone, the magnetic field alternated direction. Oppositely directed field lines came close together. Reconnection was possible. The particle intensities were higher. The plasma was more turbulent. This difference tells us that the structure of the heliospheric current sheet matters. It affects how energy and particles are distributed in the heliosheath. It influences the likelihood of magnetic reconnection. It shapes the environment that spacecraft encounter on their way to the heliopause. And it reminds us, once again, that this so-called empty region is anything but empty. So let's step back and think about what all of this means. The heliosphere is the bubble that protects our solar system. It shields us from galactic cosmic rays. It defines the boundary between the space we know and the vast unknown of interstellar space. But that boundary is not a wall. It's not a sharp division. It's a dynamic, fluctuating interface shaped by the interaction between the solar wind and the interstellar medium. Inside the heliosphere, we're bathed in the sun's influence, its magnetic field, its radiation, its particles. Outside, we're exposed to the galaxy, its cosmic rays, its magnetic fields, its neutral atoms and plasma. The heliopause is where these two worlds meet, and the heliosheath is the transition zone between them. Voyager 1 and Voyager 2 have given us our first direct measurements of this region, but they've also raised new questions. Why is the heliosheath thinner than expected? What causes the stagnation region Voyager 1 observed? How much reconnection is happening in the heliosheath? What is the true shape of the heliosphere? These questions don't have complete answers yet, and that's okay. That's how science works. Every answer leads to new questions. Every measurement reveals new mysteries. Now let's talk about New Horizons. This spacecraft is currently exploring the outer heliosphere, and it's providing us with a different perspective on the solar wind and pickup ions. New Horizons launched in 2006. It flew past Pluto in 2015, giving us our first close-up views of that distant world. Since then, it's been traveling outward into the Kuiper belt, the region beyond Neptune filled with icy bodies left over from the formation of the solar system. But New Horizons is doing more than just studying distant objects. It's also measuring the solar wind. And what it's finding confirms and extends what Voyager discovered decades earlier. One of New Horizons' most important contributions is its direct measurements of pickup ions. Remember, these are interstellar neutral atoms that have been ionized and picked up by the solar wind. They're extremely important for understanding how the solar wind behaves in the outer heliosphere. New Horizons has a plasma instrument that can distinguish between regular solar wind protons and pickup ions. This allows scientists to measure how many pickup ions are present at different distances from the Sun and how they're distributed in energy and velocity. What they've found is fascinating. At 10 AU from the Sun, pickup ions make up only a small fraction of the total ion population, maybe 5 or 6%. But as you move outward, that fraction increases. At 50 AU, pickup ions account for about 8% of all ions. And their pressure, their contribution to the total thermal pressure of the plasma, dominates. Why does their pressure dominate even though they're a minority? Because pickup ions are hot, very hot. When a neutral atom is ionized and picked up by the solar wind, it suddenly has a velocity equal to the solar wind flow velocity. And velocity is related to kinetic energy. So these newly created ions have enormous kinetic energies, far greater than the thermal solar wind protons. That kinetic energy translates into pressure. And even though there aren't many pickup ions, they carry so much energy that their pressure exceeds the pressure of the much more numerous thermal protons. This has profound implications for how the solar wind behaves. The speed of sound in a plasma depends on the pressure. If pickup ions dominate the pressure, they determine the sound speed. And that changes how shocks form, how waves propagate, and how energy is distributed. New Horizons has also measured something else important: the temperature relationship between solar wind density and temperature. In a normal gas or plasma, there's a relationship between density and temperature called the polytropic index. This describes how temperature changes as density changes. For an ideal gas that's expanding without gaining or losing heat, the polytropic index is about 1.67. But in the outer solar wind, the polytropic index isn't constant. It decreases with distance from the sunday. At 10 AU, the polytropic index is close to the ideal value. But by 40 AU, it's dropped significantly. The temperature isn't increasing as much as you'd expect for a given increase in density. Why? Because the solar wind is being continuously heated and slowed by pickup ions. As neutral atoms are ionized and picked up, they heat the surrounding plasma. But they also rob energy from the solar wind flow. This changes the thermodynamic behavior of the plasma in ways that aren't captured by simple models. Scientists have developed new models that account for this. They've shown that if you include the effects of pickup ions properly, you can match the observed relationship between density, temperature, and the amount of solar wind slowing. This is important because it tells us that the solar wind in the outer heliosphere is not a simple, isolated system. It's constantly interacting with the interstellar medium through the pickup ion process, and that interaction shapes its behavior fundamentally. New Horizons is still active. It's still taking measurements, and it's expected to reach the termination shock sometime in the next decade or two, depending on how far out the shock is at that time. When it does, we'll have a third set of termination shock measurements. And because New Horizons is traveling through a different part of the heliosphere than Voyager 1 or Voyager 2, we'll learn about the spatial variations in the shock, how it differs from place to place, how it responds to the solar cycle. This is crucial because the heliosphere isn't symmetric. It's not a perfect sphere. It's squashed and stretched by the motion of the sun through the interstellar medium. And we need measurements from multiple locations to understand its true three-dimensional structure. Beyond New Horizons, there are discussions about future missions. Interstellar probes that would be specifically designed to reach the heliopause quickly and study it in detail. These would use advanced propulsion systems, maybe nuclear or solar electric, to achieve higher speeds than current spacecraft. One concept is to launch a probe that could reach the heliopause in 15 to 20 years instead of 40. That would allow a new generation of scientists to see the results within their careers. It would also allow us to study the heliopause at multiple points in the solar cycle, understanding how it changes with solar activity. Another concept is to send multiple probes in different directions. One toward the nose of the heliosphere, where the sun is moving through the interstellar medium. One toward the tail, one perpendicular to the plane of the solar system. This would give us a complete picture of the heliosphere's shape and structure. These missions are still in the planning stages. They're expensive. They're technically challenging. But they represent the next step in exploring our cosmic neighborhood. And they're driven by the same curiosity that sent Voyager outward decades ago. There's also something else coming. In the next few years, NASA plans to launch the Interstellar Mapping and Acceleration Probe, or IMAP. This spacecraft won't travel to the heliopause. Instead, it will study the heliosphere from Earth orbit by detecting energetic neutral atoms. These are particles created when ions in the heliosheath collide with neutral atoms from the interstellar medium and exchange electrons. The resulting neutral atoms travel in straight lines and can be detected from inside the heliosphere. By mapping these neutral atoms, IMAP will create a global picture of the heliosphere. It will show us the structure of the termination shock, the distribution of plasma in the heliosheath, the shape of the heliopause. And it will do this from the comfort of Earth orbit. No need to wait decades for a spacecraft to reach the edge of the solar system. This technique, called energetic neutral atom imaging, has already been used successfully by another mission. The Interstellar Boundary Explorer, or IBEX, has been mapping the heliosphere since 2008. Its observations revealed surprising features, including a bright ribbon of energetic neutral atoms that circles the sky. This ribbon marks a region where the interstellar magnetic field is aligned perpendicular to our line of sight, creating enhanced neutral atom production. IMAP will build on IBEX's success with more sensitive instruments and better angular resolution. It will provide the most detailed global view of the heliosphere we've ever had, and it will help us answer fundamental questions about how our solar system interacts with the galaxy. But even with all of this, there are limits to what we can learn. The heliosphere is vast, it's dynamic, it's shaped by processes we're only beginning to understand. And there are regions we'll never be able to explore directly. The heliotail, for example, stretches out behind the sun in the direction opposite to our motion through the galaxy. No spacecraft is headed that way. We can only model it, imagine it, wonder what it looks like in reality. So why does any of this matter? Because understanding the heliosphere is understanding our place in the galaxy. It's understanding how our solar system interacts with the space around it, how we're protected from cosmic radiation, how we're influenced by forces far beyond the Sunday. It's also about something deeper, about pushing boundaries, about exploring the unknown, about sending machines to places no human will ever go and learning from what they find. Voyager 1 and Voyager 2 were launched in 1977. They were designed for a 4-year mission to Jupiter and Saturn, but they kept going, and 40 years later, they're still sending back data from the edge of interstellar space. They're the farthest human-made objects from Earth. They're the only spacecraft to have crossed the heliopause, and they're still functioning, still transmitting, still exploring. That's extraordinary. Not just as a technical achievement, but as a testament to human curiosity, to our desire to see what's beyond the next horizon, to our willingness to ask questions we might not be able to answer in our lifetimes. The signals from Voyager 1 and Voyager 2 take more than 22 hours to reach Earth. By the time we receive a message, the spacecraft has already moved on. By the time we send a command, the situation has changed. And yet, we keep listening. We keep watching. We keep learning, because that's what exploration is. It's not just about reaching a destination. It's about the journey, about understanding the space between here and there, about discovering that the empty regions aren't really empty at all. Now, here's something to consider. In a few more years, Voyager 1 and Voyager 2 will run out of power. Their radioisotope thermoelectric generators, which convert the heat from decaying plutonium into electricity, are slowly losing output. One by one, their instruments will shut down. First the less critical ones, then the essential ones, until finally the spacecraft go silent. But they won't stop moving. They'll continue drifting through interstellar space for billions of years, long after the sun has burned out, long after the Earth has been consumed. They'll be out there, carrying a message from humanity to whoever or whatever might find them. And if they can decipher the golden record, they'll learn about us, about a species that looked up at the stars and wondered, that built machines to explore the darkness, that crossed the heliopause and entered interstellar space. They'll learn that we were here, that we reached out, that we tried to understand our place in the universe, and perhaps they'll wonder, as we do, what else is out there? What other boundaries are waiting to be crossed? What other mysteries are waiting to be solved? That's the legacy of Voyager. Not just the data it collected, not just the discoveries it made, but the questions it raised, the inspiration it provided, the reminder that the universe is vast and strange and full of wonders we can't yet imagine. The heliosphere was once thought to be a simple bubble, a protective shell around our solar system. But Voyager showed us it's far more complex. It's dynamic. It's shaped by forces from within and without. It's a boundary, yes, but not a simple one. And that's true of everything we explore. The more we learn, the more we realize how much we don't know. The more questions we answer, the more questions we discover. That's not frustrating. It's exhilarating. It means there's always more to explore, always more to understand, always another mystery waiting just beyond the horizon. So the next time you look up at the night sky, remember that beyond the planets, beyond the Kuiper belt, beyond everything you can see, there's a boundary, the heliopause, the edge of our solar system's bubble. And beyond that boundary is interstellar space, the vast ocean of the galaxy, a place we've barely begun to explore. 2 spacecraft have crossed that boundary. They're out there right now, drifting through the darkness, sending back faint signals about a place no human has ever been. And they're reminding us that the empty regions aren't really empty. That space is full of structure and activity and mystery, that the universe is far stranger and more beautiful than we ever imagined. For now, all we can do is watch and listen, and wonder what else is waiting to be discovered in that vast, empty region we call interstellar space.